Okay, good morning to you all. I'm Ivan Rey. I'm with the Body Lab at the University of Maryland, and I'm going to present you my work on the T-cell receptor dynamics during the immune science formation. So, first, let me introduce you the B-cells. B-cells are an integral part of the adaptive immune system. They're lymphocytes that patrol the body looking for signs of infection in the form of antigen, typically presented on the surface of antigen-presenting cells. Now, the binding of the B-cell receptor to this antigen induces cross-linking and the activation of the B-cell. The B-cell then spreads in order to gather as much antigen as possible, and those cross-linked and receptors form microclusters. So the general process consists of this spreading, the formation of the microclusters, later coalescence, and then contraction portion of the process. Now the interface between the two cells is what is called the immunological synapse, and is a process that can be reproduced on an antigen-coded surface, as shown here on these same images of a fixed cell or a lipid supported by layer. So using these synthetic systems, it has been shown that the ligand mobility and the ability of cells to gather larger amounts of this antigen depends on the ligand mobility. So, for example, cells spread over a layer will gather more antigen than cells spread over glass. Also, actin has been found to play an important role, and it has been found that NWAS, for example, an actin regulator protein, plays an important role in the negative regulation of this BCR signaling by inducing the cell contractions mediated by actin. Now, at the single molecule level, there have been also several studies. Some of them have shown, for example, by inhibiting simultaneously the actin and these receptors, it has been shown that the receptors moving on actin-rich regions lower much lower diffusivity. Also, by the treatment of cells with an actin polymerization inhibitor, like Franklin, it causes a significant overall increase on the BCR mobility. So all of these works motivate us to examine in detail the dynamics of these single BCR molecules from the early events of the engagement of these receptors and the formation of microclusters and coalescence. So far, previous studies have reported diffusivities that cross over co-call orders of magnitude. And however, overall the results are shown just as overall differences between different conditions. So we really want to identify if inside those large distributions of diffusivities are there different molecular states of the B-cell receptors. Also, if there are changes over time on the mobility of the B-cell receptors and the role of different actin-related proteins on the process. So for that, our system is a supported lipid bilayer that has bioaccumulated lipids. It's coated with streptavidin and an unlabeled antibody. This system by itself will induce that cells will spread and activate. Besides that, we add in solution at a very low concentration fluorescent antibody. Now, this fluorescent antibody will allow us to follow the receptors, and we take care of the concentrations to be low enough so that we're able to identify single molecule events represented here in this single step formulation events. Now, we take 30 seconds movies of 33 frames per second, and we do this for 11 times from the very moment the cells reach to the surface. Now, something that I want to point out here on our system is that these receptors will allow the engagement with the bilayer, but they can be either just on the surface of the cell, they could be engaged, or they could be just moving around on the bilayer. So if we analyze this situation, we obtain a set of tracks, and we can construct the mean square displacement curves and obtain the diffusivity from the slope of this curve. And that provides us with a wide range of diffusivity. So, as I mentioned before, through experiments, we can try to discern what are those different types of behaviors or molecular states that we're observing. So, for example, we can use a non-bioaccumulated fluorescent antibody that will attach to the receptors, but it won't engage with the bilayer. By doing this, we can see that we get a narrower distribution and overall lower mobility. Also, if we look at the bilayer by itself, we find that there are mainly two modes of diffusion on the bilayer, and that the fastest moving molecules that we capture in our normal or regular experiments would correspond then to an antibody that is attached to the bilayer alone. So far, using, for example, a cumulative distribution plot, we can distinguish overall differences on the diffusivities after gathering thousands of tracks from tens of cells. However, there is still more information underlying these distributions. We want to know how do these evolve over time, and also we want to know how are they affected by perturbations. So a perturbation that we can also apply is, again, this electronically disruptor that will induce, as in here by this shifting in this curve, higher mobility of the receptors. But then again, the situation and the cell the cell membrane is a very complex environment. So we really want to see if there is more information that can be obtained from these tracks. So actually, that was a question that Peter Koo and Simon Mowbray from Yale asked themselves. They realized that from the simulation of different diffusive states, if they would combine and look at the overall complete distribution, they would find that it would look bimodal. So that there is an underlying complexity. So actually, through the iPoLS network, we started a collaboration with them in order to try to assess find out if we have also different diffusive behaviors in our distributions. So they developed this perturbation expectation maximization analysis tool. It is able to classify from the set of trajectories all the different diffusive or molecular states that are characterized by a diffusivity, localization error, and impopulation fraction. So far, the results, though preliminary, have been very promising. Here, for this normal condition in which we use an antibody that will engage with the bilayer, we found that there are 6 states. 6 states is not being shown here, where these plots show for these tracks the probability of belonging to on a darker color. Also, we found when we analyzed the case of the non-bioaccumulated antibody that there were some states in common that share very similar diffusivity. So this would indicate, or this would suggest that these two states would correspond then to the actual receptors engaged with the membrane. Now, this is very interesting, and across all the different conditions that we have evaluated, we have found 9 different diffusive states that have been appearing consistently depending on the conditions. So, for example, here where I'm showing the population fractions and the diffusivities, where warmer colors are higher diffusivities, colder colors are lower. For example, in the case that we're using the bioaccumulated antibody, this population of high mobility corresponding to the bilayer only appears on those cases. Also, something that was very interesting that appeared here was that by comparing our regular condition here with 6 states, and then comparing the result by adding this actin disruptor, we saw a significant decrease and even disappearance of the low mobility states, and a significant increase in the high mobility states. So, so far, all these results seem very promising, and among the future goals is to complete larger sets of data for the different experimental conditions that we've been evaluating. Also, all these experiments have been performed with an I-20 cell line, it's a lymphoma cell, and it has been really good model to characterize the imaging and the analysis. So our next step would be to start working with primary cells. They display faster dynamics. They're a better system to study as such the immunological process, and we have higher immunological relevance. And also we have access to some transgenic mouse in which some very important actin regulator proteins have been knocked out. So that's for the future, and I've been more I'd like to thank all my lab members and our collaborators, especially Peter who helped me a lot with this PM analysis, and I'll be happy to take your questions. Thank you.
We have time for 2 quick questions.
So do you think the different diffusive states correspond to different signaling clusters of the receptor? And the second point, did you look at the time decay of each and every diffusive state?
So I'll return to this slide. So actually one more. So actually something, so just the receptors that can actually engage with the bilayer are cross-linked and will be supposed to form the microclusters. Now, for those cases, for example, we have identified 2 modes. So one of them has a lower mobility, and previous studies of single molecule imaging on activated cells have found that the mobility is reduced once they enter these microclusters. And these studies are actually also very interesting because when we applied this latronculin treatment, that state actually disappeared. Now, this is just all preliminary data, but that might suggest that perhaps the movement of these receptors, engaged receptors, is somewhat actin driven.
Yeah, can you, have you tried stabilizing the actin cytoskeleton using like just plekinolide, where that locks in the actin fibers? Would that have the opposite effect?
That's among the experiments planned ahead. One of the requirements for this PM analysis is to gather large amounts of tracks in orders of tens of thousands. We're reaching those numbers with the current conditions, but it takes a while to get there.